Hi, today we're going to talk about solubility. Now, you've probably talked about solubility in the past, but today we're going to talk about an equilibrium view of solubility. So, when people talk about solubility in the first half of Gen Chem, a lot of times they'll have these solubility rules like this, where it's like these cations are always soluble, these anions are always soluble, these anions are, almost never soluble, blah, 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 blah. And there's these horrible rules that some people will make you memorize, which is not my thing. Things are not so cut and dry. So let's start by looking at an ionic compound that people say is definitely soluble when they're doing the easy version of Gen Chem. And that would be sodium chloride, just regular table salt. We know sodium chloride is soluble because we throw it into our cooking and it dissolves. We don't see salt crystals floating around. And so what's happening there is our solid sodium chloride is dissociating to form aqueous sodium ions and aqueous chloride ions. But if you go out near a very salty lake, or even in shallow spots near an estuary, what you will find is that sodium chloride actually can precipitate out of solution. So what is going on here? Well, let's think about this from the equilibrium point of view. We could write an equilibrium constant for this particular reaction. This is going to be a special equilibrium constant that we are going to call KSP. SP stands for solubility product, and I'll explain that more in a little bit. But think about what's going to go into this equilibrium constant. We're going to have our sodium concentrations and our chloride concentrations on the top. And then what normally goes on bottom is the reactant concentrations, but we just have a solid. So our KSP is just going to be sodium ion concentrations times chloride ion concentrations. And anytime you have a solubility equilibrium, it's going to look like this. It's just going to be products, because the products are aqueous ions, and you won't have reactants because the reactants are the solid that is dissolving. And so this is why it's called the solubility product, because it's just multiplication of things. Now for NaCl, the KSP is 2.48. That's a relatively large number for solubility. And so what this tells us is that the products, remember again, the products are the dissolved ions, are heavily favored over the reactants, which is the undissolved solid. So this is an equilibrium that heavily favors products. But if you have large enough concentrations of sodium or chloride, or both, then you may actually get product formation. So when people are talking about salts that are insoluble, what they're usually talking about is salts that are only a little bit soluble, just slightly soluble. We have an equilibrium again. And for every ionic compound, the question is how much of this will actually form ions, products, and how much will remain as undissolved solid. And so for this particular quote unquote insoluble compound, calcium carbonate, our KSP is given by calcium ion concentration times carbonate ion concentration, and the KSP is 3.4 times 10 to the minus ninth. Now here you see that we have a very tiny number for KSP, and that means our equilibrium is heavily weighted on the reactant side. Remember, the reactants are solid calcium carbonate, so calcium carbonate does not dissolve very much. Most of it is going to stay as the solid. So I'm going to run through a few vocabulary terms that you will hear quite a bit as we talk about solubility. First thing is a saturated solution. This is any solution that contains exactly the limit of how much of that particular solute you can dissolve in solution. A related vocabulary term is an unsaturated solution, which is a solution that has less solute that can possibly dissolve. Or another way you might think about it is you could still add more and have that extra dissolve. Then there is a thing that is called a supersaturated solution, and that is a solution that contains more solute then you're supposed to be able to dissolve. So there is a theoretical limit, and somehow we have ended up with more than that theoretical limit. And usually this happens if you change temperatures, because our KSPs are temperature dependent. And so you can dissolve more at one temperature than another. And usually the easiest way people think about supersaturated solutions is a solution of sugar water. So if you've ever tried to make a syrup, you can put like 2 cups of sugar in a cup of water and it won't all dissolve. But if you bring it to a boil, it will all dissolve, and it will stay dissolved even if it cools down. That's a supersaturated solution. So all solutions of ionic compounds are one of those 3 types of solutions: a saturated, unsaturated, or supersaturated solution. Let's now look at these important terms that are going to pop up as we do calculations. The solubility of a compound is the number of grams that you need to make 1 liter of a saturated solution. In other words, that is the theoretical limit of how much you can dissolve in water. Now, you will also hear a term that's called molar solubility, and that's the number of moles required to create a saturated solution. Your solubility will be given in units of grams per liter. Your molar solubility will be given in units of moles per liter. Molar solubility is really useful when you're worrying about reactions and things reacting in a 1-to-1 or 1-to-2 ratio or whatever. But solubility in grams per liter is normally what you find in data tables. So if you want to look up the solubility of a compound, you can go, for example, to Wikipedia, and it will give you solubility in grams per liter. It doesn't give you molar solubility. The solubility of a compound is related to the KSP. And what we're going to do here is we're going to calculate KSP from solubility, and then later in the video, we're going to do the reverse, calculate the solubility from a KSP. What we're going to do, this is a 4-step process. First, write a balanced equation for dissociation. Second, convert grams per liter to molarity if necessary. So if you're given the solubility as grams per liter, you need to convert it to molar solubility. Then you're going to take that molarity and convert it to molarity of individual ions. And then we can plug those ion concentrations into our KSP expression and calculate KSP. So let's go through and let's do that. Here we're given the molar solubility of an ionic compound, calcium hydroxide, and this is 1.06 times 10 to the minus 2 molar. So what's the KSP for calcium hydroxide? Remember, the first thing we're going to do is write a balanced equation for dissociation. So calcium hydroxide dissociates to form 1 calcium ion and 2 hydroxide ions. Stoichiometry ends up being super important in solubility equilibria. I mean, it's important everywhere, but you're going to see that these ion concentrations are actually going to be really important. Next step, convert grams to liters. We don't have to do that because we already have the molar solubility. Step 3 is to convert the molarity of the salt to molarity of ions. So we know that we have 1.06 times 10 to the minus 2 molar of calcium hydroxide in a saturated solution. What does that mean? Well, for every mole of calcium hydroxide that dissociates, we have 1 mole of calcium 2 plus. So we're going to have the same number of moles of calcium 2 plus. And for every mole of calcium hydroxide that dissociates, we get 2 moles of hydroxide. So our molarity of hydroxide is going to be twice that, 2 times that ratio, which is 2.12 times 10 to the minus 2 molar. Now we have our balanced equation and we have our ion concentrations. Let's calculate our KSP. So the first thing we need is we need an expression for KSP, and that's going to look like this. We have our calcium concentration times the OH minus concentration squared. Remember, when you have a coefficient of 2, you're going to raise it to the 2nd power. So now let's plug our concentrations in, and we get the KSP being 4.76 times 10 to the minus 6th. Now let's do another problem. Here we're given the solubility of a compound rather than the molar solubility. So it's a slightly harder problem. Here we have the solubility of lead iodide being 4.34 grams per liter, and we want to know what the KSP is. So the first step is to write our balanced equation for dissociation. And we're going to have lead iodide dissociating to form lead 2 plus and 2I minus. The next step is to convert our solubility to molar solubility. So we're going to go from grams to liters to moles per liters, and we're going to use the molar mass to do that. So we can take our solubility of 4.34 grams per liter, divide by the molar mass of lead iodide, 461.01 grams per mole, and we get a molar solubility of 9.41 times 10 to the minus third molar. Now we're going to take that molar solubility and we're going to convert it to ion concentrations. For every mole of lead iodide that dissociates, we get 1 mole of lead, 2 plus ion. So that's 9.41 times 10 to the minus third molar for lead. And then for every mole of lead iodide that dissociates, we get 2 moles of iodide. So that's 2 times 9.41 times 10 to the minus third, which is 1.82 times 10 to the minus second molar. Now we're going to use our ion concentrations to calculate KSP. So again, we're going to start by writing our KSP expression, which is going to be lead 2 plus iodide squared. And that's going to be 9.41 times 10 to the minus third, our lead concentration, times 1.82 times 10 to the minus second squared, which is our iodide concentration. And that gives us a KSP value of 3.12 times 10 to the minus 6th. Okay, so we've calculated KSP from solubility. Now let's go the other direction. This time we have a 5-step process. We start once again by writing a balanced equation for ion dissociation. That's always a good idea when you're doing a solubility problem. Then we're going to use X for one concentration and find the other concentrations using stoichiometry. Once we have those concentrations in terms of X, we'll plug them into the KSP expression, solve for X, and that will give us our molar solubility. If we are supposed to be calculating the solubility in grams per liter, we may have to do a conversion at the end to get it. So let's try a problem. Here we're given the KSP for silver carbonate, 8.5 times 10 to the minus 12th. And what we're asked for is the molar solubility and the regular solubility in grams per liter. So let's start by writing our balanced equation. Silver carbonate dissociates to form 2 silver ions and carbonate. Now we're going to use X for one concentration, and usually the default is to have X be the molar solubility of our solid compound. And then we're going to find the other concentrations using stoichiometry. So for every mole of silver carbonate that dissociates, we get 1 mole of carbonate. So that's also going to be X. And then we have 2 moles of silver, so that's going to be 2X. Let's plug those concentrations into our KSP expression. So here's our KSP expression. It's going to be silver concentration squared times carbonate concentration. So we plug in our value for KSP that we're given, 8.5 times 10 to the minus 12th, set that equal to the silver concentration squared, so that's 2X squared, times the carbonate concentration, X. Now we're going to solve for X. Everything on the right side here ends up being 4X cubed when you multiply that all together. Note that the quantity 2X squared means you have to square everything in the parentheses, or the brackets in this case. So you're squaring X, but you're also squaring 2. That is probably the number one problem I see when people try and do this sort of problem. So make sure you always square what's inside the brackets. So now we can solve for X by dividing by 4 and taking the cube root, and we get 1.3 times 10 to the minus 4th. That's our molar solubility. But now we need to calculate the solubility in grams per liter, and we're going to use the molar mass to do that. So you can calculate the molar mass of silver carbonate, and what you get is 3.2 times 10 to the minus 2 grams per liter, And again, that is the solubility. So now we have the molar solubility and the solubility. Before today, you have seen solubility as kind of a binary thing. Something was either soluble or it was not soluble, but in reality, solubility is all about equilibrium. I hope this was helpful, and I will see you again soon.